Okay. Well, first I want to thank the organizers for the invitation. So today I'm going to tell you about paramodular forms and its applications to holography and quantum black holes. But before we go into this adventure of understanding what even is a paramodular form and why you should care, let me first tell you who else cares. This talk is going to be based on 2 papers from the past couple of years that involve Alex, Joao, and Christoph. And I'll be also reporting on some work in progress that involves Alex, Christoph, and my PhD student, Beatrix. And hopefully this will be done by the end of the summer. So the premise is quite simple in this talk. So I'm interested in the framework of ADS CFT. I want to know what does it take for a CFT to be holographic, and more importantly, how can I build one? Okay, how can I design and can I craft a conformal field theory with features that are gravitational? So I'm going to be putting myself in a box more and more as this talk goes along, so I'm going to be trying to address this question in the context of ADS3, CFT2. It's not universal. Many of the things, the tools, the approaches that I'll take will not extend to higher dimensions, but I think it illustrates the point, and it complements very well with other talks that we listened during the week. So very good. So this is the premise. So I'll be discussing this in the context of ADS3, CFT2. On the ADS side, I want a theory that admits a supergravity description. Okay, so this is the goal. When you say this it already takes me on the other side of the duality. I'll be necessarily looking at conformal field theories with large central charge. Okay, so that's the basic premise. Now, the strategy that we're taking is the following. So I won't be super explicit, but here and there, I am finding inspirations from other instances in string theory where we understand ADS3. I'll be using holography quite heavily, so that's not going to be new. But the new part of what I'm going to be presenting today is how we're using number theory, okay? How we're using theory of modular forms to try to address these questions. So, have to click harder. The talk will be structured in 3 parts. So in the first part, I'll be telling you what do I mean by a holographic CFT. So I'll introduce for you some necessary conditions in order to quantify these conformal field theories, okay? They're necessary conditions, let me stress it right now. They're not sufficient, but it will be our starting point. The second part of the talk will be about implementation. So we will have these conditions, and I'll try to find theories that actually satisfy those conditions. By the time we get here, I'll be in supersymmetric land, for better or worse. But that's what I'll do. Now, the third part of the talk, I'll come back to the point of quantum black holes, trying to understand what these modular forms teach me about these objects, and in particular, how we understand properties of the black holes beyond just the area law. So let's start with this concept of holographic CFTs. So from the ADS side, this is basically my only slide on gravity, unfortunately. I really have in mind that I want the Einstein-Hilbert action plus matter, make it supersymmetric, supergravity, whatever you like. The only thing that you need to know about ADS3 gravity for the purpose of this talk is knowing some basic properties about its spectrum. So it has light states, it has perturbative states, it has the Brown-Henault gravitons, and as well it has heavy states, it has the BTC black hole, okay? Depending on the theory and the details and how you view it, there might be other types of solutions, but I'm not going to focus on those today, okay? So what we'll have in mind is that there's light states and there's heavy states, okay? Perturbative states and black holes. So from this point of view, I'm going to be imposing roughly, 2 types of conditions. It's basically just one. But let me describe what I would be meaning by a holographic CFT. So, black holes. Black holes have a large amount of entropy that is characterized by their area, and in particular, this entropy, the area law, is dominant when the size of the black hole is large in Planck units. If you translate this condition in the language of the CFT, it tells you that you need to have a large amount of entropy in a regime where the energy is comparable to the central charge of the theory, and both of these parameters are very big. Okay? So you go through your holographic dictionary, so basically it tells you, okay, the black hole entropy should be interpreted as the logarithm of some number of microstates. You can use modular invariance of the CFT to have some idea of what is the asymptotic behavior of these number of states. It gives you this very nice expression, the Cardy formula. You go through your holographic dictionary, and you find that it's equal to the area divided by 4. Great, success. Now, going from this first to the second line, one has to be a little bit careful. The validity of this formula, if you just are using, if you're only relying on modular invariance, applies when the energy is just much bigger than the central charge. So strictly speaking, you're only characterizing black holes that are very, very massive. Now, what we want is actually capture the entropy of all black holes. Okay, so I really want to justify the second line in the full regime where the black hole is big. And this is what we usually call the extended Cardy regime. So you're looking for a specific type of conformal field theories for which this expression is valid in this range, okay? So that's the first condition. Now, there's something very interesting about this condition that takes me to this perturbative regime. So a few years ago, it was noticed quite beautifully that the perturbative part of the spectrum, so these light states, they tend to not be universal, okay? Because it will depend on the details of the matter theory, of the gravitational theory that you have at hand, but actually black holes put restrictions on how many of these light states you can have. And so in particular, by either requiring the presence of a Hawking-Page transition or requiring this extended Cardy regime in the context of supersymmetric black holes, the number of light states has to at most go like e to some power of alpha. It's independent of the central charge, so C is not appearing in this formula. And this power alpha here has to be less or equal to 1. Now, I'm going to be interested, the case when alpha is equal to 1 is too much. That's basically Hagendorn growth, so I'm not interested in that case. So for the purposes of this talk, I'm looking for conformal field theories for which their light content of operators has this growth where this power here is strictly less than 1, okay? And this is what we usually call the very sparse spectrum. Very good. So now, in order to look for these type of theories, I'll do what I do best. I'll consider supersymmetric states. Okay, so we'll start focusing more and more. So I'll be not looking at any state in the CFT, just those that preserve some supersymmetry. So the object that we'll be studying is the elliptic genera. And I'll be considering the cases where the elliptic genera is a weak Jacobi form. I'm also interested in kind of capturing and characterizing theories with large central charge, so we'll use the symmetric product formula to try to get to a regime where C is large. Now, the condition in this language, in the supersymmetric language, is that I want that the number of light states in the NS sector is basically obeying this restriction. Now, I should note something very important. I'm going to be focusing on the symmetric product theories. If you just look at the partition function of symmetric product theories, they have alpha equal to 1. So they're not gravitational in the language that I'm using for today. And this is why I'm looking at the elliptic genus of this type of theories. It's a protected quantity, and so from that point of view, it doesn't matter that I'm looking at it in the symmetric product point. If it really has a gravitational dual, whatever properties it has at the gravitational point, it should persist at the symmetric product point, okay? So this is where I gain quite a lot by looking at supersymmetric instances. But very good. The spoiler now, because this sounds, for some of the experts in the room, it will sound like a very old story and familiar. So for those of you that are anxious, we can tell you very well, very precisely, which of these weak Jacobi forms satisfy this criteria. Here I'm writing squiggly, but in our papers there's equal signs because we're pretty good at characterizing this density of states. And new examples are going to be unveiled, and they've been hunting you a little bit on the side of the slide for those of you paying attention. So in any case, this is basically the picture. So imagine we have a space of CFTs. There's some subset of those that we're calling holographic. And what we're doing here is looking for those that have the symmetric product description. And we want to understand what is this interplay, what is the overlap between those theories that have a symmetric product description and that admit this holographic interpretation. Very good. So let's implement these conditions, modular forms. So from our past, this is what I've learned. I learned that supersymmetry is powerful. I'll use it. The second thing that I've learned is this concept of averaging over theories that usually goes under the name of second quantization. I want to study theories at large central charges, okay? So we're going to treat the central charge. The way I can do that, and I can understand the analytic continuation and see, is by treating it as a statistical variable. And that's what we're going to do, okay? And then the third point that I'll leave it a little bit in suspense, I hope you start appreciate it as we go along, is that I'll introduce an exchange symmetry because it's going to give us quite a lot of control. So the implementation of these three properties of supersymmetry, averaging, and the exchange symmetry is achieved by this set of paramodular forms. So what are they? They're basically functions of three variables, which can be decomposed as a sum of Jacobi forms of index m and weight m. Sorry, weight k. They're characterized by the transformation properties. They transform under the paramodular group, gamma plus of t, which basically, in a nutshell, they have modular properties and elliptic translations, which are basically the transformation properties of the Jacobi form. But in addition, this function of three variables has an extra symmetry, which is an exchange symmetry in rho and tau. So here, this p, which is e to the 2 pi I rho, is basically the chemical potential, or the fugacity that couples to the index, and the index is what you should be thinking here in terms of the central charge, that I'm summing over theories. And if you exchange the chemical potential for the central charge and the chemical potential for the energy, there's a symmetry in this modular form. The case when t is equal to 1, so there's an integer here appearing in this transformation, basically corresponds to SP4 set. Now, it's not so difficult to build these paramodular forms. They might look a little bit abstract. What are examples of these objects? But actually, Gritsenkov and Nicolin told us super easy. Really easy to build any of these paramodular forms. Even I can do it, so anybody else can do it. So basically what you do is that you grab one Jacobi form of weight 0, favorite one, pick any one that you want. And basically the Fourier coefficients of that one seed, you put it, basically controls all the data in this formula. So the coefficients here, you put them up here, and they control these powers up there via these relationships, and the resulting object of three variables is going to be a paramodular form. You're done. Now, in relationship to the symmetric product theories that I was interested in studying, they're not equal to the generating functional of a symmetric product. Basically, you can split this paramodular form into two. There's a part here that is called the Hodge factor that carries the information about the weight of the form. But then here, there's another part of the form that it's basically this generating functional for the symmetric product theory, okay? So the nice thing, though, about this object relative to this one is that this one has this exchange symmetry, and it will prove quite powerful, okay? The symmetric product generating functional does not display that symmetry, at least explicitly, because there's this Hodge factor that they differ by. But in any case, Gritsenkov and Nicolin didn't just tell me how to build paramodular forms, they actually gave me a lot of information. There's very minimal input. You just tell me what the seed is, and then everything is given for free. They also told me what the analytic properties of these objects are. I know the locations of their zeros and poles, which usually go under the name of Humbert surfaces. And third, I would not be up in the stage talking about this if it was not for Ashok Sen and his beautiful analysis of quarter BPS states in n equal 4. So he basically taught us how to extract these coefficients quite beautifully and efficiently. So the technical part of our work is basically carrying out these integrals, these contour integrals, and understanding what are the behavior of these coefficients, and we really can do it with quite a lot of precision and elegancy. So if you're not familiar with these papers, I strongly recommend that you take a look at them. Very good. So What are promising Siegel modular forms? So by promising, I mean that they meet the two necessary conditions that I discussed at the beginning. Since there might be some anxiety, here there are 5 examples. These are 5 seed functions that if I build the exponential lift, they will meet the criteria of a holographic CFT, okay? They will have this very, very sparse spectrum. There's at least 5 of them. Now you will ask me, what is so special about those 5? Well, there's 3 basic properties that they share. The most important one that I'll discuss a little bit more is the location of their poles. Okay, so they're described by this H11 Humbert surface. There's 2 other conditions here that I impose. Basically, that the degree of the pole is 2, so that's why there's a 2 here in this list, which is not crucial. And also, the list got cut up to index 6 because we wanted only paramodular forms with positive integer weight, but it's also not a fundamental property, just to cut somewhere. But okay. But the property that was quite crucial is something that benefited a lot of our analysis was actually the pole structure. And basically, if you notice in these examples, all of them start with a term that had y to the minus 1. So they were all like of minimal polarity. Okay, so that's what they share. So today, if I wanted to be very kind of modest, we really understand what happens to any Jacobi form up to index equal to 4. There's also that case of index equal to 6 that is standing alone. But our work in progress and what is going to happen anytime now, because we're getting a lot of intuition of what are the mechanics of this program, is that we'll be able to quantify all of them and just tell you in one go, these are all the weak Jacobi forms that will meet this criteria, and it will be based basically on the properties of their Humbert surfaces. Now, let's make this a little bit more concrete, flash you this slide. So this is the most famous Siegel modular form in the string theory community. It's the Gusa-Kuss form. It's the one where we know most about quantum black holes and matches the supergravity spectrum in ADS3. There's generalizations to CHL. We could talk about this form forever and ever, and I don't have the time today, but okay, it meets all of the criteria that we like. There's a second example that is more new, and it's quite interesting. So this example, for instance, involves a combination of 2 of, when I listed these 5 examples, there was this phi 01 and phi 04. If you pick a linear combination of these 2 with Jacobi forms here, this one has to be, the entry is 2 sets so that it becomes index 4 again. This one also satisfies all of the criteria that we wanted. It's not too surprising because it actually, not so long ago, recently, it appeared in a context of matching an n equal 2,2 superconformal field theory to string theory and supergravity on ADS3 times S3 times T4 modded by G, or refolded by G. So this is another example. The thing that is interesting about this example, although it involved these 2 of the 5 examples that I listed on the top, the Humbert surfaces are a little bit different, so it's H42 and H11, so it has some interesting new features from the mathematical point of view. But okay, very good. So in the last, there's also bad Siegel modular forms, so there are Siegel modular forms that you will not like. I do like this one. So this one, it's my favorite bad one. So by bad, I mean that it does not meet the criteria. It will have Hagendorf growth. The reason why I like this one, it's called chi35. It's because if you specialize it to y equal to 1 or z equal to 0, the j function appears. So I like the j function. That's it. But okay, that's a bad one. But very good. So let's talk a bit about now the quantum black holes. So we're not, basically, by now, I hope I convince you I'm not studying the empty set. That's what's happening. Okay, so let's talk about black holes. So in this context, so again, we're trying to understand the behavior of these Fourier coefficients when you have this exchange symmetry. And if you look back again to when we basically equated the Bekenstein the black hole entropy to the logarithm of the microstates. Here, you can justify this step from here to here without needing to use the Cardy regime. You use it, but then the exchange symmetry basically tells you that if the entropy was valid when E was much bigger than C, it also will be valid when C is much bigger than E, okay? Which was kind of screaming at you from the fact that here C and E come in together. So this is a case where you can have this extended black hole regime kind of for free. The exchange symmetry, this was my first motivation to study these forms. It was because the exchange symmetry that they had kind of guaranteed for me that I was going to be successful at this stage. Now, we can say something about the dots as well. So we don't have to just describe the physics of the area law. There's actually a lot that you can say about the corrections, but since I don't have too much time, let me just tell you a little bit about the logarithmic corrections, which are also, one can extract them quite systematically. So you can, because there's such an extended regime of validity for E and C, you can look at different scalings. Either E is very big, but C is fixed. They're both big and comparable, or you can look at an opposite scaling regime. The first one will be the logarithmic correction that you would get if you're just looking at corrections to the Cardy formula. The second two regimes are basically those that are relevant for VPS black holes in 4 and 5 dimensions. And the thing that is interesting about this table and that I wanted to stress is that the coefficient of the logarithmic correction changes depending on the scaling regime that you're in. So this is a case where in the supersymmetric context, there is interesting data to test and match. It's non-trivial, and it's encoded here in this table. Now, it's clear what's happening in the context of this weak Jacobi forms, how these corrections are being organized. But actually, there's more results on the gravitational side about what is the universality and robustness of these corrections. And so I think what needs to be explored in this context is a better accounting for the origin of these corrections and what do they tell us about the microscopic theory. So for instance, this year there was a very interesting paper where they extracted this logarithmic correction, which was actually completely universal if the modular form only had positive coefficients. Another object that hasn't been explored here, and now that we have new examples that fit all of our holographic expectations, is the issue of mock modularity. So you could try to understand how could you distinguish between single center contributions versus multi-center contributions and these counting formulas, and understand basically the DM set proposal. But very good. So I'm on time. This is strange. Okay. Yeah, I think there's a bias against black holes in the computer. Any case, so basically we explore these three topics. And the message is the following. So our goal was basically to try to understand this orange region, okay? So what is a holographic CFT? We have many conditions. It's not clear yet that we have all sufficient conditions, but there's some of them that are necessary. And I want to understand example. I work very much based on examples. You need to give me some concrete example, and then I can study it and understand all the ins and outs. So our goal is to build new examples, and that's what we have at the moment. We basically have new candidate weak Jacobi forms that meet all this criteria, and the task now is to actually, so for two of them, we have a home. Basically, we know what the gravitational theory is, and we understand what the conformal theory is, but now there's many more examples that don't have a home, and our goal is to give them one. So with that, thank you very much.
Questions for Alejandra? Yes.
Thank you. What is the physical origin of this exchange symmetry?
So for the case of T = 1, it's electric magnetic duality. It's due to the U duality group that you encounter in 4 dimensions. In the other cases, I don't know. So I think the second example that I gave us a good one. I think there we will also be able to understand how it appears as a U duality symmetry. But in general, I'm just exploiting it. I just said, let me use it because I know, at least from the mathematics, that it will work. But yeah.
Very nice. So suppose you wanted to go further and also capture conical defect solutions in the bulk. Have you got any thoughts on what to do for that?
Yeah, I would need to know more about the details of the gravitational theory. So, and then basically characterize those solutions, understand their properties, and then it will have to be, for now, supersymmetric conical defects, and then we will be able to say something about those in the field theory. But I think that will be, it might depend on the details of the compactification and or the background that you have, but yeah, that's quite doable.
So when you get one of these modular forms, the ones that are not studied well enough, what is the prescription to finding the gravity duo with? Like, do you have a list of steps that you need to do to?
Oh, I wish. No, it's an art.
So it's just guesswork.
I think the example where there was an orbifold, it's quite useful because then I will be looking at orbifold of maybe known cases, and then that will be a step. There's many, by now, we've gotten better and better at finding new supergravity background with ADS3 factors, and people know what the supergravity spectrum is. So if I know what the supergravity spectrum is, at least I can match the elliptic genus in the C going to infinity limit to what people call the supergravity elliptic genus. And so there's checks that I can do, but today I don't have like a recipe for like, oh, do this, and then you get your master's thesis. No.
Okay, then let's thank Alejandra again. And before we disperse for the coffee break, a small announcement or addition regarding